Okay, now we're going to look at finding probabilities and distributions. And this is all building up to when we start doing inferential statistics. It's all based on these distributions and the probabilities of getting certain values. Whenever you're looking for evidence to try to make a decision, you give different sources kind of different levels of confidence or different priorities. You have the people you trust and the people you don't trust. The people that if you want advice, you go to talk to because you think that their advice will lead you down the right path. You're not sure, of course, but there are some people you give more confidence to. And the question is, before you take action on anything, how certain do you have to be that things will turn out the way that you want? If you're going swimming, you may in a lake, you may say, I'll go out, you know, 500 feet, but at some point, my confidence in my ability to get back is going to start going down because you're thinking that the probability of you getting back the shore safely is lessening and lessening with every minute that you're out there and every extra meter that you're moving away from shore. And so when we make decisions on when to turn around or when to do things, we're basing it on certain assumptions about how likely different events are. And that's really how inferential statistics really work. It's all based on probabilities, based on an assumption that we have some kind of distribution that we can start gauging. So what I'd like you to do is go to this website, www.z-scorecalculator.com, and play around with this yourself a little bit. If you look at this, you have a left-right button that you can highlight, and that highlights different areas. You look at in the right tail area that you have 50% or a probability value of 0.5. And I can also say left, right, equal areas. And in this case, it's less than 1, negative 1.5, more than positive 1.5. I can do different areas where I can change them in each case, right? I can do the middle area that's equal, or I can do the middle area that's different. Now, what I want to do is just kind of run you through here and say, suppose that, this distribution really just represents, billions and billions of z-scores, and I've dumped them in a bag. And the frequency of those z-scores is represented by this graph that I have very few in the between 3 and 4 and negative 3 and negative 4. I have most of them between 68% of them roughly between 1 and negative 1. And I have the most right at the middle, right? As I get lower, as I get higher, farther away from the middle, the probabilities go down. So the first thing we can ask is, okay, well, because I can't talk about specific values and I have to talk about ranges, why don't I ask, what's the probability of getting a z-score greater than 1.5? Well, in order to calculate that, what I need to do is first figure out, am I looking for the area above 1.45, or am I looking for the area below? Am I looking for the left or the right? And in this case, I'm looking for the right, because I want it to be greater than 1.45. So what I can do is change my right z-score to 1.45, hit the calculate button, and I see that the probability of getting a z-score of 1.45 or greater is about 0.073. And we can round that up to 7.4. And I change the color of that just so it stands out. Isn't that nice? If I want to look at a range, I can say, well, what's the probability of getting the score greater than 2.13 or less than negative 2.13? Well, I'm looking left, right, equal area. And so I can just change this to negative 2.13. I have to make sure it's negative in this case. And I see that the probability there, total probability, see I have about 1.5% here and 1.5% here. Combined, it goes to about 3.3% or 0.033. If I say between -2 and 2, now I'm looking at in the middle, right? I'm looking between -2 and +2. So here I'm looking middle equal area. I want to say -2. Hey, there we go. And I see that I have about 95.45% in there. And if I say greater than 0.5, well, now I'm just again looking to the right, and my value is a positive 0.5. Could be negative. I could say, what's the probability of me getting something greater than -0.5? And that would be more than 50%, because I'm looking for something greater than that, a negative value, which is left of the 0. And what's right of that then has to be more than 50%. But we'll just go back to just the regular 0.5 so I can put the right answer in there. And I see that it's about 31%, 0.3. We can just go with the 0.308. Yeah, we'll just go with 0.31. What the heck. So that's really how it works. And we can do this when we're talking not just about z-scores, but about regular scores. So suppose that I have my population mean of 100 and a standard deviation of 10. I can say, what's the probability of getting a score greater than 110? Well, in order to do that and use this distribution, what I need to do is turn that first into a z-score. And again, the z calculation is my score minus the population mean, and then I divide that by the standard deviation. This gives me a value of 1. I want to know the probability of getting a score that big or greater. I plug it in. I see that it's about 15.87%. Or 0.1587. Now, we can do that the same with this other stuff. If I say greater than 90, well, again, if I calculate this, 90 minus 100 equals -10 divided by 10 equals -1. Now I want to know about greater than a negative score. It's going to be a lot more than 50% in this case, but it has to be more than 50% because I'm looking to the right of a number that's below 0. So when I look at that, the probability of me getting a score out of this population that's 90 or more, that'll happen about 84% of the time. If I switched it to less than 90, well, now I'm not looking to the right, right? When I'm asking about greater than, and only greater than, then I'm looking to the right of the value in question. If I say less, now I'm looking to the left. And in this case, left of -1 is 15.87%. If I say, well, what about between 80 and 20? I want to go 2 standard deviations above and 2 standard deviations below. What's the probability that I'm going to be in there somewhere? And all I have to do there is highlight the middle. I see that it's about 95.5% of the scores fall between -2 and +2. So in other words, if we think of these as people, 95% of the people are within 2 standard deviations of a mean, or of the mean. They're all within. Half of them are within 2 standard deviations below. The other half are within 2 standard deviations above. If I say within 10 points of the mean, now that means that I'm saying that, well, they go down to 90 and they go up to 110. If I calculate each of those, right, within 10 points of the mean, and I calculate what those z-scores are, then I'm having boundaries of -1 to +1. And if I plug that in here again, I see that that makes up about 68% of the scores. And that's exactly what this is describing. Now, that's how I find just basic all kinds of different probabilities for different ranges. Greater than, less than, greater than or less than, or then within 2 different boundaries. We can also talk about percentile ranks again. And percentile ranks, again, always represent the percentage of scores at or below a given value. So at or below means we're always going to be looking to the left. Always. Always. Now a z-score of 0, of course, represents a percentile rank of 50. And you can think of this as your percentile rank. If I want to look at the percentile for the following scores, right? If I plug in 1.5, I'm always looking to the left, whether it's positive or negative. I see that that's at the 93rd percentile. A z-score of -1, meaning you're 1 standard deviation below the mean, gives you a percentile rank of 15 or 16, about, if we round that up. And so being 1 standard deviation below the mean puts you at the bottom 16%, and that's pretty low. In some cases, if we go with -0.5, you're about a half standard deviation. That puts you at the 32nd or 33rd percentile. If your score is high, like your 3.31 standard deviations above the mean, you know, that means you're about better than just about everyone. You are at the 99th percentile, the 99.95 percentile. If I look for the percentile rank of -1.5, and this is where a lot of at-risk programs start looking at students and stuff, well, now we're talking about, excuse me, about the bottom 7% of people in the population. And 7%, well, 6.68% of the scores are below this z-score value. Now, we can calculate percentile ranks for individual scores then, again, not just the z-scores. So given our mean of 100 and our standard deviation of 10, what's the percentile rank for the following scores? Well, if I take 110 and I turn it into a z-score using this formula, 110 minus 10, or 110 minus 100 equals 10, I divide that by 10, that gives me a z-score of 1. And if I plug that in for the percentile rank, I see that that's at the 84th percentile. If I go with 120, well, now my z equals 2, right? And if I plug that in my z-score calculator, I see that now I am at or above 97.72% of the population. Get rid of that. There we go. If I go with 80, well, if I go with 80 minus 100 is -20, divided by 10 is -2. So my z-score equals -2. And if I plug that into here, the percentile rank of that is 2.28. And I can keep going with these. If I have a z-score of 9, or a raw score of 90, then my z-score equals -1. Excuse me. If I go and I check that out in my z-score calculator, I see that it's at the 15.87 percentile. And I can do the same thing with score of 75. My z-score would be -2.5. Plug that in. And so when I see that it's really, really low, and I can, likewise, I can go with 130, and that gives me a positive 3.0. Oops. And if I plug that in, somebody 3 standard deviations above the mean scores at the 99.87 percentile. And so when we say what percentage of people scored above each score, I can answer that. I can answer that by just subtracting each one of these from 1. So if this person did as well as or better than 84.13, I know that, well, the remaining 15.87% of the people did better than this person. If for any particular score I want to know what percentage of people scored below that level, that's a question I can't answer with the same amount of precision, because the percentile rank, again, includes everyone who scored at their level as well. And I don't know how many people or what percentage of those people are at that level. In the case of z-scores, it doesn't really matter because, like we said, each individual value takes up virtually no space at all. So I won't ask you this question on an exam or anything, but it is something to think about, that in reality, I can't really say a percentile rank doesn't tell me how many people I did better than. But when we're using distributions like this, it pretty much says that exact thing, meaning that because the percentage of people who have my exact ability represent an infinitely small amount of the distribution, I can treat it as essentially nothing, and so on. But technically, it's not right. So I have a few more of these for you to do on your own, and I'd like you to do that. Take the next quiz that has you give the answers to finding the probability of getting different scores for different distributions and things like that. And then we'll move on to making probabilistic decisions as the last section.